When a helicopter is flying, the blade of the helicopter makes three types of motion. A motion like this. The blade also goes up and down. And the blade also does this type of motion. This type of motion is measured by an angle that is called the azimuth angle, which is equal to omega times t. Omega is the angular frequency of the rotor. The way this azimuth angle is measured is this angle is 0 when the blade is closest to the tail, it's 90 degrees here, it's 180 degrees there, and so on. Usually the azimuth angle is measured in a horizontal plane, but sometimes it is measured with respect to the plane that is perpendicular to the vector that makes an angle of alpha degrees with respect to the vertical. It is measured with respect to this plane where this angle is alpha. That angle alpha is called the rotor angle of attack, and an alpha, in this case, in this notation, -5 degrees means an angle of 5 degrees forward. The other type of motion is given by the angle that the blade makes with respect to the plane that is being used to measure the azimuth angle. And that angle is called the flapping angle. It's denoted by beta and depends on T, or it depends on C, and essentially it's taking care of this motion of the blade going up and down with respect to the plane that measures the azimuth angle. The other angle is the pitch angle, which is equal to theta 0 minus theta c cosine of c minus theta s sine of c plus theta twist times r over capital R. Little r is the distance from the center of rotation to a particular section of the blade. Capital R is the radius of the blade, and theta twist is the difference in pitch along the radial part of the blade. For the blade, usually the pitch at the tip is smaller than the tip at the beginning. That change of pitch is called theta twist. An example of such a value is -10 degrees. We're going to consider the following problem. We're going to assume that it is given to us the velocity of the helicopter, the weight, the drag, and the lateral force, and we want to find beta of t, periodic, a periodic function that describes the flapping motion of the blade, and we want to find theta 0, theta c, and theta s. This is the input by the pilot, and with the property that the thrust produced by the blade when it rotates balance the weight, the drag, and the lateral force, and also it makes the helicopter fly with this velocity. Notice that we have this picture here. The weight is a force that goes down. The drag is a force that is opposite to the motion. And the lateral force we can think of perpendicular to these two forces. This is the lateral force Y. And we want to produce a force, maybe a thrust, that balance the three forces. The sum of these three vectors is equal to 0. To start, in order to understand the difficulty of this problem, let's define u sub t equal to omega times r plus v times cosine of alpha times sine of c. Notice that ut is known if we know r and c. We are also going to define up equal v sine of alpha minus mu minus r times the derivative of beta minus beta times v cosine of alpha cosine of c. This mu, which is the induced velocity, is in red because it has not defined before. We need to find that mu. In order to find the mu, we need to solve this equation. The equation is a b c times theta ut squared plus ut times up equal to 8 pi times r times mu times the square root of b squared plus mu squared minus 2b times mu times sine of alpha. Let me write on red where terms that has the mu in it. Here we have mu, here we have mu, here we have a mu squared, and here we have a mu. When you think about this equation, we notice that mu depends on r and c. Once we have r and the azimuth angle c, we notice that in this equation the only unknown is mu. This equation is not impossible to solve, but it's challenging. And one way to solve this equation is by squaring both parts of the equation, and then we end up with a quartic equation of mu. And then we need to decide which of the potentially 4 solutions of this equation is the one that we want. Notice that the mu has a physical interpretation. The induced velocity is the velocity of the air that comes down when the blade hits the air. Then this blade rotating at every r and at every azimuth angle, there is a velocity of the air going down, which is called the induced velocity. It depends on r and it depends on c. Then this is regarding the difficulty of finding mu. What else do we have? We have these 3 vectors, and we want to find the flapping motion of the blade. Once we have beta of t, we can think about the circle that best fits the motion of the tip of the blade. The tip of the blade doesn't move in a circle, but we can think about the best circle that describes the motion of the blade. We want that circle to be in a plane that is perpendicular to the vector given by the thrust, which is the opposite of the sum of these 3 vectors. Then we want the tip of the blade to be approximated by a circle that lies in a plane that is perpendicular to the thrust. That's because we want to balance these forces. This ends up being an equation on the first linear approximation of beta of t. Beta of t, or beta of c, can be written as beta 0 plus beta c cosine of c plus beta s sine of c plus beta cc cosine of 2c, and so on. Then this equation about this circle, it ends up being an equation of these 2 coefficients. In order to continue describing the problem of finding the periodic function beta of t and the input of the pilot, the theta 0, theta c, and theta s, let's define dt equal to 1/2 times a times c times theta ut squared plus up times ut times dr. Then with this definition of dt, we have that when we do the integral with respect to r of dt, this is essentially the thrust that this blade is producing at a particular azimuth angle. This is equal to a function in terms of the azimuth angle. But since we are assuming that there are b blades, then when we do the average, which is 1/2 pi times the integral from 0 to 2 pi times b times t of c, we want this average to be equal to the magnitude of the thrust. We want this to be equal to the square root of w squared plus d squared plus y squared. This is the third equation that we want to be satisfied. We have this collection of equations to find the mu. We have this equation concerning the circle that best describes the motion of the tip of the blade, which is an equation on beta c and beta s. And we have this third equation. The last family of equations that we want is the following. Let me erase this part here. This is concerning the second equation. Is an equation of these two. If we define the integral of r dt with respect to r, this is the moment of the thrust. The thrust of the blade is producing a moment on this blade, and we want to balance this moment. We want this moment to be equal to the integral with respect to r of m times omega squared times r squared times beta squared plus the integral with respect to r of n times r squared, the second derivative of beta. This is the moment of the centrifugal force, and this is the moment of inertia of the blade. We want to balance the moments, and then we want this to be true. But when you think about this equation, we are integrating with respect to r, and all the expressions that are here, they depend on r and c. Then this becomes a function in terms of c. For every azimuth angle, we want this equation to be true. It may look like this equation is a linear, non-homogeneous linear equation in terms of beta. You can think that this equation can be written like this, like a of c times the second derivative plus b of c times the first derivative plus c of c times the function beta equal to a function k of c. It may look like it is an equation that is linear and non-homogeneous, but this is not the case. The reason this is not the case is because to find the mu, you need the beta, and to find the beta, you need the mu. Sometimes you assume that this mu is constant, or that this mu is something that is independent of the beta, and in that case, you end up with a differential equation that is linear on beta. But the way it is presented here, this equation is not linear. The reason is that these coefficients, they have beta because the mu is there, right? Then this is not the case. But we have our four family of equations that needs to be true. For every azimuth angle, we want these two functions to be the same. Then we have four families of equations. One is we want the mu to satisfy this quartic equation. We want the circle described by the flapping motion of the blade to be in a plane that is perpendicular to the thrust, and that ends up being an equation of beta c and beta s. We want the magnitude of the thrust, which is given by this integral, to be equal to the square root of w squared plus ds squared plus y squared. And for every c, we want this equation to be true. Okay, this is it for this video. I just wanted to explain the difficulty of the problem to find the beta of t, the theta 0, theta c, and theta s. We want to find beta, theta 0, theta c, and theta s such that all these equations are true.